Good morning, afternoon, and evening to folks tuning in from around the world, and happy World Quantum Day. I'm Derek Wang, a research scientist at IBM Quantum, and I'm subbing in for Zlatko this week. Welcome to the IBM Qiskit Live Quantum Seminar Series. This is episode 118, and I'm glad you guys are joining us on time. In a minute, we'll be hearing a talk by Minnich from Caltech. But before we begin with introductions, let's give everyone a couple of minutes to tune in. So in the meantime, for those who are already here, and as is tradition, why don't you share where you're tuning in from? I see Ron already posted beforehand, coming from the north of Chicago. And something else we can also, oh, here we go. We got Paul from Portland, Bihar from India. So really, we're spanning the globe this time. Cool. So this seminar takes place every Friday at noon Eastern time, and it's hosted on the Qiskit YouTube channel, and you can subscribe below. You can always go back and catch up on anything you missed, but you can only ask questions here, live, now, during the seminar, with Tal from Israel, Ali from Finland, Luca from Italy. So really everywhere, and Ross from New York City. All right, so I think it's about time we begin. I am thrilled to roll out this latest episode. It's dedicated to you, the research and academic communities. I'm your guest host, Derek Wang, for people just tuning in from the IBM Quantum Research Org. And today I have the privilege of hosting Minnich from Caltech. He will speak about the experimental realization of a measurement-induced entanglement phase transition on superconducting quantum processors with mid-circuit readout. He is a professor at Caltech. His research interests include low noise microwave instrumentation and quantum simulation on superconducting microwave systems. He received his bachelor's from UC Berkeley in 2006 and his PhD from MIT in 2011. So take it away, Austin.
All right, great. Yeah, thanks so much for the introduction and opportunity to speak. I'd like to thank the audience throughout the world for tuning in. And this is a really special seminar series because, as Derek was just saying, we have audience from really all over the world. And it's great that everybody gets to come and talk about these really interesting topics. And so it's my pleasure to be able to talk about particularly our realization of measurement-induced entanglement phase transitions on superconducting hardware. All right, so if you're tuning into this series, you probably know about and are excited about the rapid advances in the capabilities of quantum hardware. So for example, the quantum volume, which is a metric of the capability of a quantum computer developed by IBM, has been rapidly increasing for a variety of near-term quantum computing platforms. And this chart is showing that value for ion traps and its rapid increase. In addition to quantum computing platforms, there's also been advances in other types of hardware relevant for the quantum ecosystem. For instance, quantum networking enabling the generation of long-distance entanglement. Now, for near-term quantum computers, which is a central focus probably for many of us, a particular type of realization of that device based on superconducting qubits has made tremendous strides in the past 20 years. So these superconducting qubits are fabricated from superconducting metallic films patterned into a certain shape to give the functionality. And that's what's shown in this image on the left. And from the initial development of this type of device around 20 years ago, there's now devices with tens of qubits, and there's very ambitious plans to further scale this technology towards thousands of qubits. And this is the roadmap that IBM Quantum has published, showing a very exciting program towards that or thousands of qubit scale quantum computer. So naturally within the community, there's been interest in understanding what we can do with these devices. And in science and research, we're interested in physics and quantum systems. And so naturally, we're wondering what type of physics we can study with these near-term quantum computers. So in the community, this question has been addressed intensively, particularly since about 2016. And this time series here shows the remarkable progress in the field of quantum simulation. So if we go back to 2016, only 7 years ago, the state-of-the-art quantum simulation was a few qubits, fewer than 10 entangling gates. If we fast forward to today in 2023, the state of the art is tens of qubits and hundreds of 2-qubit or entangling gates. And we've moved from just calculating ground state properties of simple molecules like H2 into simulating the dynamics of various quantum phases and the Fermi-Hubbard model and so on. And what the community overall is trying to get to is physical quantum advantage, meaning the case where we can learn something about a physical system that would be difficult to learn without the quantum computer, meaning with only classical or computers or other resources. So that's the goal. Now, the challenge is, despite all that progress, there's still some pretty significant limitations of today's quantum computers. The traditional paradigm for using a quantum computer is shown on the left here. So you execute what's called a unitary circuit, where these blue rectangles are indicating entangling gates, and you do a bunch of them according to some algorithm. And at the end, you measure the qubits, and you repeat that many times. And then the bit strings, consisting of zeros and ones, have the answer that you're looking for in them when you process them. Now, if you look at this example circuit here, you'll notice that in this example, there's 6 layers of those blue rectangles. And that number of layers is referred to as the gate depth. Due to imperfections in the gates that are applied, as well as decoherence of the qubits themselves, the maximum gate depth of today's quantum computers is something like 50 to 500 layers. And while that's certainly much improved compared to 7 years ago, it's still turning out to be not quite enough to do the most interesting quantum simulations. And so that has people in the field looking for alternate ways to make use of these quantum computers. One way to overcome or maybe sidestep this gate depth limitation is to expand the concept of what a circuit looks like on a near-term quantum computer. So traditionally, they consist, like you see at the left of the screen, these unitary circuits where you have gates followed by measurement at the end. Recently, though, there's been tremendous interest in hybrid circuits, where the measurements are not just confined to the end, but rather they're interspersed throughout the circuit next to the gates. And that case, or the mid-circuit measurements in this picture are indicated as these pink diamonds. So if this type of circuit is possible, the theory community has told us there's tremendous or interesting novel phenomena that can occur. For example, there can be phase transitions where the quantity of interest in the phase transition is entanglement, just like temperature or pressure occurs in kind of more ordinary phase transitions. In addition, it's theoretically and experimentally now demonstrated that quantum states with very interesting entanglement properties can be prepared with asymptotically reduced resources, meaning in different scaling with the system size. And so, of course, both of these things are very interesting, and these provide a route to kind of sidestep this gate depth limitation through the leveraging of mid-circuit measurements. And so I'd like to tell you about a particular effort in that direction, in which we realized a measurement-induced entanglement phase transition on a superconducting quantum processor. And if you look in the chat, I believe the archive link is there, and that link has all the details that I'm going to describe in this talk and more. So if you are further interested, I encourage you to have a look at that link.
Awesome.
So today,
quick question before you move ahead. I'm wondering, what is the connection between an entanglement phase transition and then a physical simulation of a real system?
Well, you can imagine entanglement phase transition. It's let's see. It's a particular type of physical phenomenon that can occur and is described by a particular Hamiltonian and I guess it's, in my view, no different than simulating like a Fermi-Hubbard model, which can correspond to some, for instance, atomic system with particular types of interactions between the atomic sites. So when you add mid-circuit measurement, it's kind of indicating some specific interaction with a larger environment, and in that sense, it's describing a physical system. So the um, rate of measurement corresponds to the degree of interaction with the environment.
Okay, great. Thank you.
Yeah. Yep. Thanks for the question. So today, basically, I'm going to describe this work and then our recent efforts to go beyond what we did. And so first, specifically what I'm going to talk about is how to actually implement random hybrid circuits on hardware, considering the realities and practicalities of the device. Then I'll describe the demonstration of that measurement-induced entanglement phase transition and the evidence that we have for it. And then finally, I'll describe scalable ways that we hope can characterize these measurement-induced phase transitions, which I'll abbreviate as MIPTs. So that's the agenda for today's talk. And let's move into the first topic, which is how to actually realize these circuits on hardware, considering the realities that the quantum computer doesn't always do what you want it to do. And there's certain theoretical circuits that we'd like to implement, but we can't because of just limitations of capability. All right, so just as a way of framing that problem, first I'd like to talk about the concept of these entanglement phase transitions. So this axis on the left is measuring qualitatively the effect of measurements on the quantum many-body system. So if you have no measurements, then when you apply gates, the system becomes increasingly entangled. And as we'll see in just a second, the entanglement entropy, which measures how entangled the system is, has a particular scaling with the size of the system. And that's referred to as extensive. If you're familiar with thermodynamic terminology, extensive, scaling with the system size, or volume law. And we'll see an example of that in just a second. On the other hand, if you measure sufficiently fast, you can actually lock the system in a measurement eigenstate, and that effect is known as the quantum Zeno effect. And so that's the other extreme in which you measure very frequently. Now, what's interesting is the intermediate regime, where you can have unitary evolution interspersed with measurements that aren't too frequent, corresponding to the bottom of the slide. So in this case, the theory community has found that there's distinct volume and area law phases possible, which I'll describe the terminology in just a second. So it's in this intermediate regime that we're interested to search for these entanglement phase transitions. Okay, so in a little more detail, what do I mean by volume law and area law and entanglement phase transitions? So this plot is of entanglement entropy, which is again a measure of how entangled a system is, versus system size. For instance, number of qubits. And if you have very few measurements, you're going to be on this volume law line where the entanglement entropy scales linearly with the system size. So that's kind of at the top of the chart. On the other hand, if you measure sufficiently rapidly, where this measurement rate P is greater than some critical rate P star, then the entanglement entropy scales sub-extensively, meaning less than the extent of the system size. And that case is referred to as the area law. And so schematically, it looks like that curve at the bottom of the figure. Now, what's really interesting is if you have a measurement rate P, which is about equal to that P star, the system exhibits critical behavior, such as scale invariance, that's associated with your kind of normal liquid vapor phase transitions. So that same type of critical behavior occurs in the entanglement properties of this quantum system. And it's been proposed to detect this transition in various ways. So this is a plot of measurement probability P versus measurement strength. And what we're looking at is the variance in the entanglement entropy. So you can see away from the transition at the lower left and the upper right corner of the figure, you have this low or blue color, which means there's not a lot of fluctuation in the entanglement entropy. But when you get close to the transition, there is a lot of fluctuation indicated by the yellow, and the transition occurs at that red line. Okay, so it's been proposed that we can detect this transition by the increase in the entanglement entropy close to the transition.
Austin, we have a question. What is
Sure.
the unit of measure for entanglement entropy? Or maybe in other words, how can we interpret this?
Essentially, the entanglement entropy is measuring the, I guess in the mathematical sense, the Schmidt number, but that's just indicating the number or the degree of connectedness between two distinct regions of the system. So if you have just a pure state, there's only 1 degree of connectedness because there's no entanglement, and so the entanglement entropy is then 0. But for an entangled system, for instance, think of like a Bell state, the degree of connectedness is greater than 1, and so then you have an entanglement entropy that's bigger than 0. Is that helping to answer the question?
Yeah, I think that makes sense. Thank you.
Okay. And we'll see in just a few slides the actual equation of how, and I'll show exactly how we get the entanglement entropy. So if you can, if it didn't quite answer your question, just hang on and we'll be there in just a minute. Okay, so our goal is to realize these phase transitions. There's been a related work on a purification transition, which is published in 2021, as you see on the right of the screen. And we're essentially trying to build on this work because this work did not use mid-circuit measurements. It did a lot of really neat things. At the same time, it deferred the measurements to the end using ancilla qubits. And what we were trying, in the spirit of trying to demonstrate the capability of near-term hardware, we would like to realize this phase transition with really mid-circuit measurements on non-trivial system sizes, meaning more than 10 qubits.
Awesome.
So that's the goal.
I expect you'll get to this later, but there's a question in the chat about when you measure something, don't you destroy the quantum properties? And this has to do with the measurement strength. And I suppose you'll talk about that, but just flagging this now in case you won't later.
Yeah. Yes. I think if you let me get into it, check with if the person can comment again in about 10 slides. Let me get through it, and then we'll see how it's going.
Sounds good.
Yeah. Okay. So first of all, why is this a good time to study this particular physics, entanglement phase transitions? Well, a big part of the reason is that the hardware engineers are hard at work implementing high fidelity and fast, meaning sub-microsecond, mid-circuit measurements. And the reason is that you really need mid-circuit measurement to do error correction to make logical qubits composed of many physical qubits. So there's been a lot of effort to implement this in hardware, and I'm not going to go into the details, but just to point out some of the works and the tremendous amount of hardware effort that's involved in making this mid-circuit measurement actually perform as we need. So these are just some relevant papers. I won't go into the details, but this is just something to know about. Okay, so now that we have this capability, how do we actually take the theory diagrams of these mid-circuit measurement random or hybrid circuits and turn them into something we can study on a quantum computer? So there's a number of problems in taking the circuits as they're given and actually taking them into the quantum computer. So first of all, these mid-circuit measurements in this diagram you see here are present, but there's a lot of them. there's 2 layers per time step where you're looking at the screen at one time step. Mid-circuit measurements take about a microsecond. So if you have too many of them, your qubit will decohere. And so you want to have as few as possible. Now, in addition, this is a random hybrid circuit, so we need a particular type of random unitary called a Haar uniform unitary, and the particular definition doesn't matter so much. The main problem is they need 3 controlled knot gates in depth. Again, those controlled knots take 200 to 300 nanoseconds. So if you have too many, it takes too long. We'd like to have fewer. Finally, there's periodic boundary conditions typically assumed in the simulation, and the qubit topology on actual devices doesn't really lend itself to periodic boundary conditions. So we need to figure out what to do about that. So here's an example, or this is the circuit that we ended up with, which is addressing those concerns, but still shows the physics that we want to see. So one time step is indicated in the dashed box. There's these blue rectangles, which are the unitary gates, and then the diamonds are the mid-circuit measurements. Now, the measurements will be of different types. So one is just the familiar projective measurement. And to respond to the earlier question, what the projective measurement does is project the qubit into either 0 or 1. So it does project out the quantum state on that one qubit, but remember there's lots of other qubits, and those quantum states are unaffected. Now, we also can have what are known as weak measurements, and I will have a slide for that a little bit later on because it takes some time to explain, but it essentially controls the degree of projective nature of the measurement by a unitary called V. So in one limit, the measurement does nothing, and in the other limit, it's a projective measurement. And we can continuously tune the strength by some parameter. These measurements are placed on each qubit with some probability P. And so that's how we do, that's what the circuit looks like. Now, the 2 qubit gates, what we find is that we can approximate the true random unitary with a simpler version where there's only one controlled knot gate. And evidence for that, just in case you're an expert in the audience, is shown here. This is just the frequency of the eigen phases and the spacings between the correct one in orange and the approximate one that we implemented in blue. So for all practical purposes, they're close enough. Okay, so besides the entanglement entropy, and I'm going to describe how to get that in the next slide, I just want to note there are other ways to observe the entanglement transition, and actually they have some attractive properties which avoid some issues with the entanglement entropy. So we would like to use these other methods if we could. For instance, there's the bipartite and tripartite mutual information between disjoint subsystems, and that quantity exhibits a peak at the P value of P where the phase transition occurs. So this is a really nice parameter in theory, but the problem is in practice, it requires tomography on disjoint, meaning these disconnected subsystems, and you need a prohibitively large number of qubits, kind of exceeding 20. So unfortunately, although there's some nice theoretical properties of such a measure, we can't really use that. We have to do the entanglement entropy. Okay, but that's still okay. So here's how you get the entanglement entropy. You apply these time steps, and when you're satisfied, and in just a second I'll show what that means, but at the end of the circuit, you do tomography on a subset of the qubits. Tomography means you measure in all different bases and you reconstruct the density matrix, which is called rho. And then using the equation on the right, you can compute the entanglement entropy once you know that density matrix rho. And here alpha is indicating the order of the Renyi entropy. So to answer the earlier question regarding how you actually get entanglement entropy, this is it. And you can see if the density matrix is corresponding to a pure state, you'll have a trace of just 1, and the log of 1 is 0, and so you get entanglement entropy of 0. Okay, now how do you know when you've performed enough time steps? What you find is, this is a classical numerics shown at the lower left, that the first order entropy, for instance, is the y-axis versus the time step. And over time, the system saturates the sum value of the entanglement entropy. And you can see there's distinct cases for the volume and area law, which are determined by the measurement rate P. And so you evolve the system until you reach close to that saturated value. And then once you hit that point, then you do tomography, get your density matrix, and get S. Now, here's the really challenging aspect of this study. To see the really interesting phase transition effects, it turns out we have to reconstruct this density matrix for every mid-circuit measurement bit string. So if you look at the circuit on the left, all those diamonds are going to produce zeros and ones. And for each distinct combination of zeros and ones, those are shown at the right of the slide, we need to get a density matrix. And then we can get S. Once we have all those S's, we compute the entropy mean and variance. And that's how we get those quantities that I showed before with the entanglement entropy variance. But the problem is there's exponentially many of the distinct quantum trajectories, meaning those bit strings, meaning it scales exponentially with the number of mid-circuit measurements. And so that means there's a lot of calculation that has to be done. Okay, so again, just to summarize, the steps are for each mid-circuit measurement bit string, you have to do this tomography on a subsystem of the qubits, meaning just part of the system. From that, you reconstruct the density matrix. From that, you get the entanglement entropy. So that's kind of the process. Okay, so how do we reconstruct the density matrix? Well, what you get out of the quantum computer are expectation values of polystrings, meaning x tensor y, tensor x, tensor z, or the long strings of poly operators tensored together. And you measure a bunch of those, and you get some expectation value in a vector. And then we do a least squares reconstruction, where we are trying to find the density matrix that will produce those expectation values while enforcing some constraints on the properties that a good density matrix should have, like positive semi-definite and so on and so on. And when you do that, you get a density matrix for one mid-circuit measurement bit string. And you have to do that for every single one. Okay, so clearly this is extremely expensive. How can we practically carry this out? Well, we have to make use of some tricks to reduce the cost by non-asymptotic but appreciable constant factors, which really make the difference. So one of those tricks is that you reduce the number of circuits you need to run by measuring commuting polystrings simultaneously. And for time, I'm not going to go into the details except to say that there's well-established theory that you can always find groups of what are known as mutually unbiased bases and find a bunch of strings that commute, and then you can measure them at the same time. So we implemented this algorithm to find those mutually commuting strings. We then append a circuit like that shown at the middle bottom of the slide to ensure that we're measuring those commuting strings. And that's how we get savings of about 4 to 5 times in the best case. And that is literally the difference between executing these circuits for a calendar year versus 2 months, which is in the hardest case what we actually did. So this was really important to the practical outcome.
Do you find that the fidelities or like the accuracies of your measurements are significantly affected by having to do those extra gates at the end to entangle and then measure in those bases?
The appended circuits are usually pretty shallow, and they're Clifford gates, and we don't really find any issue associated with that. There's lots of other things that are much more important.
Got it.
Yeah. Okay, so how did we actually carry this out? Now that we have the circuit protocol, how do we actually do it? Well, there's just no way around that. The experiments take a lot of time. And these experiments took about 5,000 hardware device hours, which corresponds to about 200 hardware device days. And if you are interested, the breakdown of that time is available in the supplementary information in that archive link. And so why does it take so long? Well, you have to average over random circuits, meaning the different random gates and placements of the measurements. There's about 50 to 100 of those. For each of them, you could have 2 to the 10 to 2 to the 16 trajectories, meaning those mid-circuit measurement bit strings. For each of them, you need to do the density matrix reconstruction, which is about 10 mutually unbiased bases. And then for each of them, you need at least 1,000 shots to get enough averages or information to get the expectation value for the density matrix. So when you think about it like that, you can easily see why this could take a lot of resources. All right, so here's some representative devices that we used. One of them is IBM Hanoi, and a really absolutely critical development that fortuitously happened when we were in the middle of this study is that devices with about 750 nanosecond mid-circuit readout times became available. And that was absolutely critical because the previous generation of devices took 5 microseconds. So that factor of more than 5 decrease in the time to do the measurement allowed us to do more layers of measurements by the same factor. So that was really important. And here's what a circuit looked like generally. This is about up to 14 mid-circuit measurements interspersed with these unitary gates. Okay, so let's move on to show that we actually did realize this entanglement phase transition. All right, so what we're going to do is go back to this plot of entanglement entropy variance. We're going to consider ourselves in the projective limit, which is the right of the figure, and we're going to take that vertical slice indicated. Here's the entanglement entropy on the top and the variance versus measurement rate P. This is if you just do the circuit for 4 qubits, this is what comes out of the quantum computer. Now, there's some known issues that are routinely corrected. For instance, the readout accuracy is not perfect. You can fix that with readout error mitigation. And so that leads to this change. The second mitigation that we can do is we note that if your measurement rate P is unity, meaning you're measuring at every time step all the qubits, you should get 0 entanglement entropy because you're in a pure state. But what you measure is not that. You don't measure 0. So what you can do is subtract that residual entropy, which is due to hardware imperfections, from all data points. And if you're curious, again, in the supplementary information, there's details of this procedure. So if you do that mitigation, you get the final blue symbols. Now, did this mean that we saw the transition? Just wait a few slides and we're going to go into some detail about that. But what we can say right now is that this is indeed showing the signatures of entanglement crossover, like that shown in the the left of the screen. Okay, another prediction is that the entanglement entropy should have some distinctive scaling with system size in the volume and area law phases. The left plot is showing that a second order Renyi entropy versus qubit number L, and you do see that you get the proper scaling in the extensive and sub-extensive regimes. Okay, now here's where we have to take a step back and understand what we're measuring. So we executed these circuits, and we ideally, what should have happened is that for the 2 qubit gates that we implemented, whatever gate angle we wanted was exactly performed, and over the 1,000 shots that we did, the gates were exactly the same every time. Okay, but in reality, that didn't happen. The gates that we applied are not exactly what we want, and there's fluctuations in the angles from shot to shot. Similarly, for measurements, the ideal case is that whatever the proportion of ones and zeros that we expect, we should get that. The measurement qubit should be exactly projected to the either 0 or 1 state, and the other qubits are not affected at all. But in reality, so we don't always measure the correct outcome. The qubit that got measured is not exactly projected, and other qubits are affected by crosstalk. And that's not all the imperfections that can happen. The qubits can decohere according to their T1 and T2 times. You can have 1 qubit gate errors and so on. It's really important to supporting our claim of the entanglement phase transition that we understand the role of these imperfections. So over the next few slides, I'm just going to describe some representative examples of the effect of 2 types of errors, 2 qubit gates and measurements. So first up is the 2 qubit gates. All right, so the actual gate that we implement is approximately modeled in our model as the ideal gate plus a depolarizing channel. And for the experts, there's this equation where the depolarizing strength is parameterized by lambda. And if this doesn't make sense, then that's completely fine. It's not necessary. And basically the issue is that there's random fluctuations from shot to shot because the gates that you execute are not exactly the same every time. Okay, and that corresponds to mixing of the quantum state on each trajectory. Now here's the problem. The entanglement entropy, mean, and variance are affected by depolarizing strength in our model lambda due to classical entropy contributions from noise. Okay, so what that means, first of all, the entanglement entropy that I described to you, how we're getting it, on mixed states, it also includes this classical mixing entropy. And that's not the quantum one that we are trying to find. These plots are just illustrating that this is a different measure of entanglement that we can do classically, but not on the quantum computer, called the squashed or CMI entanglement. And it excludes this classical mixing entropy. So on the left is the expectation value and the right is the variance of the entanglement entropy for different depolarizing strengths. So in the blue case, we're just measuring the quantum entropy, which is what we want. But if the depolarizing strength gets larger and larger towards 1, we eventually don't measure any quantum effect. It's all just classical mixing entropy. And that's bad. We don't want that to happen. So let's see how that imperfection affects our measurements. So this is a plot of entanglement entropy and variance left and right versus P. So the ideal case is this blue line. But when we have kind of a few percent depolarizing error, we see that the curves are kind of qualitatively similar to the ideal case. The entanglement entropy, mean, and variance both increase due to these classical entropy contributions. there's a shift in the detected phase transition rate, or P, due to noise. And the overall conclusion is that the shape of these curves is maintained with depolarizing errors. And so that's a possible confounding factor, and it means to really support our claim of the phase transition, we have to look for quantitative agreement with the noiseless theory in the experimental data. So that's the important conclusion here. We need quantitative agreement with theory. Okay, so now let's go into measurement errors. So we have this circuit, and we're going to model the real measurement as a combination of two things. Of course, there's the measurement that we want to happen, the ideal one, plus a local quantum error on the qubit that was measured, a non-local quantum error on the other qubits, and then a readout bit flip probability that we call Q. And so that will account for the various types of imperfections in the measurement. Now, measurement errors have a variety of effects. The first is that it affects the tomography because it will lead to an incorrect density matrix and hence entanglement entropy. That's certainly severe, but the more severe one is that it mixes quantum trajectories, meaning you're supposed to get an entry for one mid-circuit measurement bit string, but that measurement is actually getting applied to a different trajectory. And so that's very bad. So let's see what happens to our measurements when we have these types of errors. First of all, how bad are these things, these imperfections? Well, the bit flip probabilities Q are normally by IBM characterized through calibration circuits. So we have those. What about these local and non-local errors on the qubits and the spectators? So what we did to characterize those is execute some benchmarking circuits where we measure the local error by applying a sequence of measurements with a depth d and then doing quantum state tomography, QST. Then we characterize the non-local error similarly, but we do the QST on the spectator qubit. All right, so then we compare this to noise simulations to estimate the strength. So the gray rather, is the raw data. The red is readout error mitigated. And then the grayish lines are strengths of depolarizing channel, which allows us to estimate this local and non-local errors on the order of 1 to 2%. So that's a number just to keep in mind as we go forward. Okay, so let's see what these readout bit flip errors do. Again, here's the ideal case in blue. And here's Q, the bit flip probability up to a value of 10%. Now here, what you can see is even qualitative features in entanglement entropy can disappear with sufficiently large readout errors, because we're looking for that peak in entanglement entropy, and you can see on the right, that red curve basically doesn't have it anymore. So the experiments are most sensitive to readout bit flip errors, and we estimate we can tolerate about 3% of bit flips with readout error mitigation, and the hardware we're estimating it's about 2%. So we're within but close to that limit. Okay, so we'll just finish up this section with the measurement errors. And for time, I won't go into a whole lot of detail except to say the error budget is more forgiving for non-bit flip measurement errors. So what we're really concerned with is those bit flips. And basically, we're well within the tolerance for these types of errors. Okay, so now let's return to the data. And remember, we're looking for quantitative agreement with a noiseless theory to support the claim of the entanglement phase transition. And that's indicated by this black line. And you can see we do basically get that agreement. In addition, with this scaling with system size, The black line is the theory without any noise, and we're again getting good agreement with that. And so from these observations, we conclude that we did in fact see the measurement-induced phase transition in the experiments. Okay, so for time, I want to highlight this, but maybe not go into the full detail. I do want to point out in the paper, we took a slice in the horizontal direction in addition to the vertical direction to show this measurement-induced phase transition. So the horizontal direction in purple means we fixed the measurement probability P, but we have changed the measurement strength. And now getting back to what that measurement strength is, for the experts in the audience, there's the equation which shows exactly what this unitary V does. But that's not really necessary. The main point is that this V kind of interpolates between two limits. For eta equals 0, there's no coupling and no measurement between the two qubits. But for eta equals 1, there's an effective projective measurement on the system qubit. For intermediate eta, we're doing something kind of in between, and that's what we mean by weak measurement. So we can tune eta and look for signatures of this transition. To actually implement this, it's a little more complicated because, first of all, the unitary V normally requires 2 C naughts, which is, we'd rather have fewer. It turns out that in our case, we can get away with just 1 C naught, which we did. And then the qubit topology becomes more of a problem because you need ancilla. So in an example layout like this one, there's these 2 groups of 6 qubits where you have 3 system ones in white and 3 ancilla in gray. And then there's these unused ones in dark gray. So those are kind of examples of how we arrange the qubits. All right, so we can, again, look at the entropy S and the variance of entropy at the bottom. These are the numerics without any noise for different values of P 0.75 on the left and P equals 1 on the right. And this is for 3 qubits. So if you just take the data out of the quantum computer, you get these gray symbols. And then if you apply readout error mitigation, you get really nice agreement with the noiseless theory. And in this case, because the system size is so small, it turned out that we didn't need to use the residual entropy correction. Okay, so we have indeed observed these signatures of the entanglement crossover with weak measurements.
Austin, I'm not sure if you've mentioned this already, but when you were looking at the phase transition for increasing the measurement probability, why did you have to do with 14 and then here you can get away with 3? Are these 2 different sweeps somehow more robust or less robust at different system sizes?
Yeah, it just depends what you're looking for, in the sense, if you're looking for the scaling of entanglement entropy with system size, then of course you have to have a range of qubit numbers. But if you're looking for the signatures of the transition when tuning other parameters like P or eta, you could just choose to have a certain number of qubits and then sweep that parameter.
Got it.
It's just different kind of indications of the transition.
Okay. And then in this case, I guess you can't do more because we're limited by connectivity in that case.
Exactly. Yeah.
Okay.
Right.
Thanks.
Yeah. All right. So to finish up this section, the last thing we can do is look for that critical behavior that I mentioned at the beginning of the talk. So again, for experts, the scaling of these different properties near the critical point is predicted to have this in scale invariant form where there's these particular critical exponents, gamma and nu. And so the idea is that when you rescale everything appropriately, so the following will happen. Oops, sorry. Okay, so after rescaling, if you take a bunch of data from all different qubit numbers and you scale them, you'll actually collapse all the data onto the same curve if there's this critical transition. So the raw data are what's shown here. This is entanglement entropy versus P for different qubit numbers. And they don't look really that special, but when you scale them in a very particular way, you find they actually collapse onto the same curve for all these different values of L. Okay, and you get some exponent, which is just kind of interesting to know. And you can compare this again to noiseless theory. And even though there's there's some degree of finite size issue with these numbers of qubits, it still agrees quite well with L equals 12 numerics. So this is again a good indication that we've seen phenomenological critical behavior on quantum hardware. Okay, so I have just a handful of minutes left, and I'm just going to briefly describe some current efforts which are in progress. So I'm just going to show you kind of the status of a more scalable way to characterize these measurement-induced phase transitions. All right, so to do what I showed you required 32,000 qubit hours, 200 qubit days, basically. And the reason is to characterize the entanglement entropy and find the phase transition, you need to do quantum state tomography for that reduced density matrix. And you have to do that for every trajectory. That requirement is known as post-selection. That requires exponential resources to verify this measurement-induced phase transition. Now, in the theory community, this problem has long been known, and there's many people working on more efficient ways to figure out if a phase transition actually happened. And so I'm just going to describe one of those proposals and our efforts to implement it. And so now I'm describing the work of Yaodong Li and Matt Fisher, and their paper is at the bottom of the screen there if you'd like more information on it. But the basic idea is that these measurements, we can think of them, the pink diamonds in particular, as yielding information about the state of the quantum system. And so the idea of this protocol is, suppose we have two circuits, and they only differ, for instance, in their initial state. So in the bottom circuit, there's these T gates in front, which change the initial state prior to the part of the circuit with the blue rectangles and the pink diamonds, but otherwise they're the same. If you have insufficient number of these mid-circuit measurements, you don't get enough information about the initial state, and you can't figure it out from that limited number of measurements. On the other hand, if you measure sufficiently frequently, you actually can discern that the initial state of the circuits is different through those measurements. So that's just the high-level concept. And there's a way you can actually quantify the degree to which you can distinguish those initial states. So suppose you have the two circuits, again, identical except for those green squares. Each of these circuits produces a mid-circuit measurement probability distribution. Call it Q for the top one and P for the bottom one. You can compute a quantity known as the cross entropy chi, which measures basically how close these distributions are. And what's really interesting is that this chi signals a phase transition in the entanglement. So this is a plot from their paper of chi versus P. And basically, chi goes to 1 in the volume law phase for small enough values of P, because the mid-circuit distributions are not affected by the difference in initial state. But for high enough measurement rates, the distributions are different, and this value of chi goes to some value less than 1. And in the large qubit number limit, you would get basically a step function in this value of chi at a particular measurement rate, PC, but for finite size systems, you see a crossing in the chi for different values of L. Okay, so that's what this says. Chi goes to 1 in the volume law phase. In the area law phase, chi equals 1, since we can distinguish the initial states from the measurements. Okay, and this is an interesting way to characterize the phase transition because the classical simulation of the hard quantum circuit requires exponential time because the number of these so-called T gates scales linearly with the system size, and classical simulations time scales exponentially with the number of T gates. So this circuit that you're looking at is actually hard to simulate classically, but it can be done on the quantum computer. All right, so again, we're faced with a situation that we need to take this circuit and implement it on a quantum computer. The idea is that you have this hard circuit, you execute it, you get a bunch of mid-circuit measurement bit strings. You then use a classical computer to treat the easy quantum circuit, consisting only of these Clifford operations, which are classically simulable. And from that, you can compute the cross entropy, and then this whole procedure is classically tractable with the help of the quantum computer, but without the quantum computer, it's hard. Okay, so there again some details for time. I think I just want to highlight. We try to reduce the number of C0 gates. The typical number of mid-circuit measurements in these circuits ranges from around 5 to 20. The hard circuit just consists of applying T gates at the beginning, and the easy circuit is a Clifford product state, and that's the only difference. And here's just an initial result. This is a noiseless emulation using Qiskit, chi versus p for qubit numbers from 4 to 10. And you can see there is indeed some indication of a crossing, which is this would be the signature of such a phase transition. This was averaged over 2,000 circuits and 1,000 shots per circuit. And so you can see this phase transition in emulation, not on the hardware quite yet.
You can't do this for changing the strength of the measurement, right? Because that would result in a non-Clifford, like all zero initial state circuit.
Right. Yeah. To my knowledge, you cannot. Yes. Okay. I think you're correct. Yeah.
Okay. Cool.
Okay. But for the more kind of normal or more common or typical case, which involves just changing p, then it is applicable. Yeah.
Got it. Thank you.
Yeah. Okay. So I'd just like to finish up with some future directions. Beyond, well, first of all, for mid-circuit measurement phase transitions, there's a lot of interest in the theory community about how to characterize them without requiring this exponential scaling. So I just talked about one of them, but another really interesting idea is to make use of feed forward. And feed forward is where you can conditionally implement a gate depending on the outcome of the mid-circuit measurement. So that's indicated by the red and yellow measurement boxes. So in the case that you got a yellow box, you don't do anything. But if you get a red box, then you apply an X to the qubit. And if you add that capability as kind of an extra tool in your toolbox, it turns out you can see some interesting phenomena with respect to phase transitions that you can't otherwise see. And it turns out that in OpenQASM 3, this capability is now available. And so it's quite interesting to think about taking some of these theory proposals and translating them onto the device. The second area is in the preparation of novel quantum states using, again, measurement and feed forward. And so this is an example shown here. What this diagram at a high level is showing is that you can produce a GHZ state, which is a highly entangled state, in constant depth, meaning independent of the number of qubits, by measuring alternate qubits and applying feedback depending on the measurement outcomes. And in that way, you can get to this really interesting G8C state in just a few layers, independent of the number of qubits. And so that's an example of what I referred to at the beginning of preparing quantum states with asymptotically reduced resources. So I think there'll be a lot of activity in that area going on as well. Okay, so to sum up, we have realized a measurement-induced entanglement phase transition on superconducting quantum devices. And what we believe is the real advance is the demonstration that this mid-circuit measurement capability is good enough to start to explore this physics, which is beyond just the typical unitary circuit, but really expands the types of physics we can study on near-term devices. With that, I'd like to thank the group and particularly acknowledge Jinming, who is the lead author of this work, Dr. Mario Mata at IBM, who is really instrumental in getting the hardware runs done. IBM particularly for just being great collaborators and having a lot of really fantastic people to work with, and the funding from Department of Energy. Again, thank you so much for your attention, and I'll be happy to answer more questions.
Great. Thank you so much, Austin. That was really great. Super clear and informative. We do have a few questions in the chat I'm hoping to pass on here that you could answer. We'll close out after that.
Sure.
One question is from Ron. Is there a mechanism for increasing the number of ancilla qubits per mid-circuit measurement, and how would that affect the fidelity of the measurement? And I guess I am interpreting this in like one of two ways. One, can you use ancillas to do error mitigation for the mid-circuit measurement, like the readout errors? Or could you use additional ancillas with your like mid-circuit measurement where you vary the strength, and then maybe it's just another way to control the strength by having more ancillas, rotating it in like another axis or something?
Yes. Let me say that it's conceivable, although I have not thought about that in the sense the weak measurement has a specific definition, and that's what's kind of been followed in the literature. I'm sure there are more complicated ways to do it. I'll just point out that there's practical issues associated with getting the necessary topology to do that, meaning if you have a chain of qubits, okay, I guess you could have two ancilla maybe, but then the central qubit can't couple to anything else, right? So it gets challenging to find qubit topologies which are compatible with that case of multiple ancillas.
Yes.
Basically what it means is you need swap gates, which are very detrimental or hard to implement.
Yeah, I guess no qubits have the connectivity of 4, basically, and so then you can't have two.
Well, it depends. Like I guess IBM has typically done this heavy hex architecture, but there are other devices out there which are kind of a square lattice, and there you would have that kind of connectivity. Mm-hmm. So it's certainly possible. Just with the devices we had been focusing on, it was more challenging.
Yeah. We have one more question here. It's, can you comment on the recent Google AI experiment on the similar topic and the possibility of experimentally studying this measurement-only transition?
Sure. I mean, there's a number of people now who are trying to observe this type of physics. The Google quantum AI one, I'd have to really read it again before I can comment on it. So I kind of want to hesitate to do that. I will point out that on ion traps, there's been some measurements or some studies in which there's measurement plus feed forward for state preparation. And so that's an example of that second future direction I talked about. So I think there's clearly a number of efforts by academic groups as well as industry in leveraging mid-circuit measurement as a resource for this purpose.
Awesome. Thank you so much. Thanks again for coming, Austin. He is taking graduate students, so if you're interested in pursuing this kind of work in the future, definitely apply. Thanks for tuning in. Subscribe to the Qiskit YouTube channel, and see you next week. Thanks.
Thanks, everybody. Thank you.